I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew Falkowski, and I'm at the University of Utah with Dr. Taylor Sparks. How's it going?
Life is good, man. We are talking about a super cool subject today. There's all sorts of chemical reactions. We would love to have them happen, but they're too slow. They're too energetically blocked. And so we are going to dive into the big bad world of catalysis today.
Yeah, and it's an interesting topic because we know good catalysis materials. Platinum, gold, and silver are great, but they're also really expensive. And so the open challenge is, how do we find new, lower cost catalysts?
Which is why we're going to need the best and brightest companies out there to help not only build predictive models for these things, but then experimentally make them. We're not just going to predict stuff. We're not just machine learning people. We're going to try and make them. We're joined by Eike van Vugt, our friend. If you listened 2 episodes ago on VS Particle, you'll remember him. And we're also joined by Larry Zitnik from Meta's Fundamental AI Research Wing. So Larry, do you want to do a quick introduction of yourself?
Hi, I'm Larry Zitnik. I'm a research director at Meta as part of the Fundamental AI research team. Just so everybody knows, my background is in machine learning and computer vision. So I'm not a chemist, I'm not a material scientist, but I've been playing one for the last 5 or 6 years.
Fantastic.
Almost graduating.
Yeah, almost ready to get my
honorary
PhD at this
PhD,
point.
man. You're there. In fact, I'm just blown away that Meta, I'm just so curious, like, why is Meta in the materials game? I think it's amazing that you are, that some of the very best catalysis research on the planet is coming from a social media company. What's going on there?
Energy is important. I mean, you probably have heard, that, all this work on AI, and data centers, et cetera, like energy is something that's top of mind. Sustainability is something that's top of mind. So, as part of the AI team, this is something that, I personally, 5 or 6 years ago when we got into this, is like, how do we have impact on climate, energy, sustainability, et cetera? And if you look around the space and you see, like, where can AI have the biggest impact? I thought it was, chemistry, material science. That was the place to be. And that's where I got started. And that started off as a collaboration with CMU, but we can talk about that later if you want. But the other thing that I think is important to know is that material science is not just important for sustainability, but it's important for other applications as well. So our team, we don't talk about this much publicly, but we also work on materials for AR devices, augmented reality glasses.
That's right.
And that's something that Meta, as you know, is also very interested in.
Well, we are so fortunate and glad to have big companies like this who are not traditional material science people realizing the value and getting in the game. And we're also joined today by Eike. Eike, if you listened to our episode,
Yes.
Is it 2 ago? I think number 96 or something on
VS
spark ablation, which is a rad technique. If you haven't listened to that, quick hit pause, go back and listen to that one, because that served as a really good introduction for today's episode. Because here you've got the big brains over at Meta who are going to be building some really cool models to help predict materials. But we have so many of these AI and materials papers where they predict things and then they never make them. What's unique about the paper we're going to cover today is they went out and made it. And they did it with our friend Eike's help over at VS Particle. So check that episode first. Eike, how are you doing?
I'm doing fine. Looking forward to discuss the work we did in the past 1.5 years.
Real quick, Eike, how did you two connect? How did Meta know to reach out to you guys at VS Particle for this technique?
It's maybe best to ask that question to Larry, because we received the request, I think, from University of Toronto, I think.
So what happened was in this project, I was thinking, okay, we just have to get a bunch of materials to synthesize, and then we're going to go test them for, different catalytic properties. And as I said before, I'm not a material scientist or chemist. And I thought, getting the materials, you just go buy them off a shelf somewhere, right? Easy peasy. And it turned out that everybody informed me, no, this is actually the problem. Synthesizing the material was like the hard part.
That's the hard part.
Yeah, exactly. And that's when we at least I personally kind of freaked out. I was like, I didn't realize how hard this is going to be. So we, after trying a couple of things that failed, we were like looking around, and Eike and VS Particle had just published a paper. and I forget which one that was, but it showed a hint of promise. I'm like, we have to reach out to them. Like maybe they could help us. Because at the time we reached out to, we scanned everywhere. We reached out to like 25 different companies, all asking them, could you create a small amount of these sets of materials? And all of them were
Keep
like,
dreaming.
no, like exactly. Like we'll make you a lot of one material, but if you're asking us to make, hundreds of very small quantities of these materials, like we don't want to do it. And really only about 5 or 6 companies responded to us. And we gave them all test samples, and BS Particle is the only one that, to be frank with you guys, came through.
Killer. Well, we will come back to talk more about the synthesis and the experiment, but let's set up the stage a little bit more.
Yeah, so maybe just set the stage. We can talk a little bit about catalysis in general and why it's so important. Catalysis fundamentally is about lowering the energy barrier for certain reactions, making reactions that wouldn't otherwise be favorable become more favorable, or maybe speeding up those reactions, having them happen at a much faster rate. And this touches on a lot of different areas. It can be things of trying to produce certain chemicals, but there's also a lot of environmental concerns that they can potentially address, taking waste streams and catalyzing less harmful reactions. In fact, in our cars, catalysis is happening all the time.
Yeah, absolutely. Right? Carbon monoxide is a lot worse than carbon dioxide, so that's the whole point of that. Now, Meta is interested in a couple specific reactions. You're interested in the hydrogen evolution reaction and the oxygen or the CO2 reduction reaction. Do you want to talk about why you picked those and why they're particularly relevant?
We've been focusing on reactions that are relevant to, climate problems, energy, etc. One thing that's particularly interesting to us is renewable energy storage, because that's something that is pertinent to Meta, as you might imagine, because we want to use a lot of renewable energy, but the sun doesn't always shine, wind doesn't always blow, so we need to figure out a way to store that energy to make sure, our data centers can potentially run 24/7, on sustainable energy. And CO2RR, that's about taking CO2 and then using that to create other products. And what's nice about that is, if you think about that in the entire ecosystem, it's a way to make money from capturing CO2. Gotcha. So if we can get a way to make, the capture of CO2 more economical, then that's good for everyone.
It's a win-win.
So exactly.
Okay, so I understand now why you want to work on those, but you picked a really hard problem because the catalysis space is massive. And you guys should know it because you're involved in the Open Catalysis project, right? The whole point of that is that you generated a massive computational data set looking at DFT, right? Of a gazillion materials, right? I'm exaggerating, but it was a lot, right? I think we're in the tens of thousands or something. And then you're saying it's not just the materials, but it's the different facets or faces, right? Like what sort of crystal plane also matters. And then it's the different chemicals that interact with that plane. And then it's where on the planes, like all of a sudden something that didn't sound too crazy, like 20 or 30,000 different materials, sounds insane. I think the final number I saw is that you had, like 600 million or something different considerations to sort of account for, which is pretty bonkers. So you have a big design space and trying to then pair that machine learning effort where you've got a bunch of simulations for maybe hopefully useful metrics, things like absorption. Now you have the daunting task of saying, okay, in this massive palette, hundreds of millions, right? Let's say, how do we actually pick which ones we're actually going to try and make? And then how do you actually make them and measure them at scale where you can test your model out? That's a hard problem. And that is the point of today's paper, which you guys have dubbed OCX24, right? The Open Catalysis Experimentation 2024.
Yeah, and in addition to also predicting all of these different properties, there's lots of environmental concerns too. I remember there was an interesting talk from someone at one of the oil companies. They're also looking into catalysts. And one of the big problems is that they can come up with something that's theoretically really good and performs really well at the bench. But as soon as you put it in an actual environment, under real conditions, all of a sudden the real world effects of things like fouling come into play. And all of a sudden this great benchtop performer is a dud.
So explain fouling for us. What is that?
Catalysis relies on interactions between the different molecules and reactions that you're trying to catalyze and the materials and their surfaces. And so if all of a sudden those surfaces get gunked up with other things that are in the
right.
environment, you lose catalytic active sites. And that becomes a problem. All of a sudden your effectiveness goes away. And so maybe you can clean those sites, but not always.
All right. So Larry, with that sort of background that you have this enormous computational resource that's been just begging to be actually, put rubber to road and actually tested out. Tell us how you actually designed your framework for testing this. What were some of the considerations that you guys had?
Well, our overarching goal was, as you said, we want to take, all that computational work we did and discover, is this actually informative of what we see in the lab if we do actual experimental studies, right? Because it doesn't really help that much to do all this computational analysis if
Right.
it isn't informative of like the lab experiments. So when we think about this problem from a machine learning perspective, we wanted those lab experiments to have like certain properties. And some of these properties were lacking in the data that already existed out there. And a big one is there's no negative results, or it's hard to get negative results.
Tell me about it.
Because if we want to train a machine learning model, we want to filter through like tons of different materials, right? We need our model to say like, this is a bad material. And we need the model to say, this is a good material. And if all you have are positive examples, then it's going to think everything's positive. So that's one thing we wanted to do. The other thing is we wanted to create a data set which had as much diversity in it as possible. Like if we could only predict, properties for like a narrow band of different materials, then it's not going to be that useful. So as much as possible, we wanted to have like a really diverse set of materials so that way, hopefully, fingers crossed that the models would actually be predictive of, catalysts across,
new
a broad
stuff.
spectrum.
Yeah. And how did you define diversity?
So a couple different ways. One is, just elemental composition, like which elements are in it, that sort of thing. Another one was we tried to make like an approximate estimation of what we thought those different catalysts would produce. Now, this is really rough, but that way we made sure we didn't just, pick a whole bunch of materials that all produced hydrogen, let's say. We want some materials that produce, C1, C2 products, things as well, because we need that diversity in the data set. So again, the models can actually be predictive if, you want to predict C2 products, that sort of thing. You can't just have a bunch of hydrogen producing, catalysts. So that would be that. The other thing we didn't do is we did stay in a fairly narrow band of, intermetallics, because we thought that those sort of materials were easy to model computationally. So we didn't do things that are kind of more complex than that, like high entropy, that sort of thing. We didn't explore oxides, as part of this work. We'll hopefully do that as part of a follow-up work. So there is like diversity to basically as diverse as possible as our current synthesis techniques allow us to be, is to be the practical answer.
Fantastic. So I like this. When I'm reading your paragraph in your paper, you're talking about, okay, if we're going to try and make these things where the thesis of what you're trying to do, you've got it right here, say, OCX24 is where we're going to try and perform experimental studies that have been specifically designed to aid AI models in mapping computational properties, your DFT data, over to real experimental results, which is, I think, a phenomenal goal. But you say to achieve that, we've got to have a couple things happen. First off, you have to have diverse materials, which you just mentioned. You have to have positive and negative results, which you mentioned. You also say that it has to be evaluated consistently, which is absolutely true. You have to be able to rely and get reproducible results. And it has to be on industrially relevant conditions that can be scaled. I was curious about that one. Are there techniques that you ruled out? You're like, hey, as cool as that might be, atom probe's pretty awesome for making it just the right, arrangement of things. That's not scalable. So I'm curious to hear about that. How did you, and that probably leads into why you selected spark ablation and chemical reduction.
Exactly. There's two critical parts to this. One is that the synthesis technique that we were using, we were hoping to use synthesis techniques that could actually be scaled up. And that's one reason to work with VS Particle. And this is, they're actively working, on achieving that. The second thing was we wanted to use current densities, which were relevant for industrial processes.
Yep.
From, what I understand, a lot of times, experiments, academic experiments, et cetera, are done at lower current densities, but industrial conditions generally will have higher current densities. So we wanted to make sure that the experiments that we ran also went to higher current densities.
Yeah, and I think there's an interesting point here as well, is the need for actually performing your own experiments in a controlled and consistent way. We often think about pulling data from the literature, but it's really hard to control for all of the experimental conditions that are being used there. And all of a sudden, you don't know if your model's not being predictive because this data point was produced under some wacky conditions, or maybe you don't have overlap in terms of the current densities you're looking for. So it makes a lot of sense to actually produce your own consistent sort of benchmark data set that you can use.
That was maybe something that I really was surprising me. I really expected that if you have such a strong large language models, you can scrape all the papers and you will get by itself a very, very valuable data set.
We're getting closer. The problem is that the academics who are doing the work are doing it in very different ways, right? For example, something you point out here is that, okay, if you're going to do this on catalysis, there has to be a substrate, and you guys are using this gas diffusion layer, which in your case, you're using a carbon-based material. Well, as soon as you do that, like that sort of rules out some synthesis techniques. For example, you mentioned in the paper that you had to throw out carbothermal shock synthesis because the GDL, the gas diffusion layer, wouldn't have survived it. And the problem is that in the literature, you see apples to orange comparisons. There's just too many different ways of measuring things that it's not like a data set that's uniform enough to build a model on top of it, because there's fundamentally different stuff going on.
It's also really hard to control the quality of that. Like, how do you assess, without being an expert yourself, the quality of a given synthesis method?
So maybe talking about synthesis, that's also why I'm very positive that we see a general consent and a general search among some of the top PIs to really nail down on the same synthesis and really build this bridge between those different labs so that they can do the same synthesis or reproduce the same synthesis. And I think that is very important, because now everybody is, let's say, doing their own fancy stuff. And everybody,
and no one else can reproduce it.
Yeah, but that really doesn't really bring, let's say, progress. It's just keeping you in work, keeping you in science, continuing your work, but it's not really, let's say, moving forward. In the same way what you see, for example, in the semicon market, where you have a very strict guideline and the whole market is doing their part to really make the final stuff happening. And I think that is really what we would like to achieve also in the catalysis.
So one thing I like that you point out in the paper is like, okay, it's not just enough to be able to make a bunch of different materials. The other aspects, like the microstructure, you need to control for that. So you point out that the thickness, the porosity, the inhomogeneity, those should be held constant if you're really trying to draw a conclusion about the material itself. And spark ablation has a unique ability to control for those things, which makes sense. Is that also the case with direct chemical reduction?
Not to the same degree. And it's one of our assumptions, because what we found with the spark ablation actually had higher correlation than the chemical reduction. And one of our theories is that's due to the chemical reduction. Exactly. Is like this nanoparticle sizes, et cetera, are not as consistent.
Yeah. Interesting. I was going to ask, actually, did you do like one-to-one comparisons, making the same compositions and looking for what the error or the shift is between those, between chemical reduction and the spark ablation?
We did. One of the examples you can see in the paper is our baseline, which is copper. And you can see the differences between the different techniques on copper. We have a couple other examples too. We should probably do a more thorough analysis of them, though, to see, what the correlations are. But that was one of the hopes, was having two synthesis techniques, is to see like how much variation did you have between the two different techniques? Like, how would this, if you do train a model, is it going to generalize to a new synthesis technique? At least this gives you like some indication if that would work or not.
Yeah, I wonder if there's like a correction factor you can develop out of that. Something that came to mind as I was thinking about this is in machine learning and in a lot of computational sciences, there's this idea of benchmarking, where you can basically have a standardized set that you can benchmark all these models against. But in material science and in the literature, that often doesn't exist just because of how different all these synthesis conditions are. Have you thought at all about potentially using this platform for a way of actually benchmarking catalyst materials, where scientists can submit their new, compositions or chemistries or structures that they've invented to this to actually benchmark against the growing experimental set that you have?
We'd love to do that. The trick is we need to make sure that the testing procedure is up and running, done consistently. As one postdoc, a PhD student graduates, a new one comes in and does it exactly the same way. And I think that's kind of the holy grail, what we would want to do. I think when you think about benchmarking with this paper, there's another benchmarking which I think is super important, which is there's a lot of computationalists kind of coming up with new theories, new ways of basically making predictions of what they see experimentally. And then they'll have their own novel experimental results to then justify their new computational approach. And we're hoping that this allows people to basically benchmark their computational theories, approaches in a way that's consistent, because everybody will be then benchmarking against the same experimental results.
Yeah. Well, before we move on to how you use the ML models and actually tested things and talking about the results, I do have a couple more questions about the experimental stuff, maybe two. First off, you tested a lot of compounds. This was not just like a couple, like hundreds. And when I get into the details of how you actually made the measurements, they're not like super fast. These things take basically like an hour per compound, it sounds like, because you tested a bunch of different current densities. You have to wait 10 minutes a piece. Like, I don't know how many you can do in a day, but you mentioned that it is a parallelized screening, and I see why. Because if you can do hundreds, and let's say you can do 8 samples in a day, it's going to take you a long time to test all these things. So what did you have, like a bunch of the same setup running so that you could do 4, 5, 10 at a time or something?
Exactly. I think there's an image in the paper. You can see there's multiple setups of, the same kind of process being run in parallel.
Oh,
To
yeah.
be
I see
honest
it
with you,
now.
though,
I see it now.
yeah. I mean, the postdoc Chi-Hoon, who ran all the experiments, he is, like, hats off to him.
Phenomena.
I mean, he was working 24/7 to make this a reality. So there's a lot of
Give that
blood,
guy a
sweat, and
bonus.
tears. Yeah, exactly, to make this a reality.
Okay, so that was my
Yeah.
first question. Very cool that you can scale. This is scaling in a way that your typical lab isn't able to do. The second question is that you guys tackled a really hard and very controversial subject, which is automated X-ray diffraction. This has been, we don't have to get it in today's episode, but this is a hotly debated thing on whether you can actually do this. And for people that aren't familiar with it, we should do a standalone episode on refelt refinement. But essentially, the way that X-ray diffraction works is you measure a spectra, which is telling you diffraction of the phase that's present. You don't know which phase is present. So what you do is you make an assumption about the phase, you fit that pattern, and you see if it fits or not. So it's inherently a challenging process because you could come up with any number of phases to compare against. It's essentially always an unfinished problem because you could always compare something else. And even if you have a phase, you can tweak that phase, like change the lattice parameter, change the occupancies. This is something that's typically done with the hand of an expert. It is very hard to automate it. I've seen some attempts to automate it, and you guys have done that. You don't say much about it, and I would love to learn more about your efforts to automate X-ray diffraction.
One thing I want to stress too is that the characterization is super, super critical to this study.
Yes.
Because if we don't know what material we made,
all your conclusions are out. Yeah.
Yeah, I mean, like the computational models. What structure you're going to even use for your computational models if you don't have that characterization? And that's something that makes a lot of existing data sets hard to use because you don't have that level of characterization of the materials. And we found, as part of the experiments that we thought we were making X, but we ended up making Y. It'd have a different composition, different structure, that sort of thing. So this characterization was super important. To be frank with you, I don't personally know as much about the high throughput XRD that was done.
Okay.
It was done at the University of Toronto. They did have a setup there to do it. But I was more involved in the analysis of the XRD patterns themselves.
Well, it's the analysis that is the more interesting thing to me. High throughput, the X-ray, I've seen that done. I don't have a problem with that. But the analysis is hard. For example, one of the things you point out, you're like, okay, we considered it, you looked at multi-phase matching. In other words, when you refine the refined structure has a composition, that should match the XRF. That seems like a really good thing to do. The fact that you're doing multiple XRFs to do the comparison, that's a good thing. But you say that you're using this sort of quick and rough refelt fitting, which is, and essentially saying like, if you get 78% of the phase mixture that matches, we'll call it good. I wonder how sensitive catalysis is to impurities, if 70% is good enough, or if skeptics will say like, this whole thing is based off of an assumption of purity that is not borne out. I don't know. I would have concerns and questions about this, although I'm delighted that a capable company like Meta is taking it on because it's a hard problem to solve.
It is really hard. And I think it's an open question. And, it's one of the ones that we're hoping. I don't think the data exists here for us to really answer that, question definitively because, at the end of the day, XRD is ambiguous. You can have multiple, phases that look very similar from XRD. You have a hard time telling which one is which. A lot of the structures that we were matching against are structures that are computationally found, but have never been synthesized. So you don't know if they'll actually be real.
It could be a new structure.
Yeah, it really could be. And we just don't know. Like, we don't want to give an XRD is just a signal towards that. You don't want to be saying like things definitively, like, yes, this is definitely that structure. But what it does do is it tells you, I look at it not as saying this is definitely the right structure, because I don't think we can claim that just with XRD. But what I do think it does is it tells you, is this definitely not the right structure?
Yeah, okay.
Because you can usually pull out, like, this is multi-phase or this oxidated, or something along those lines. You can pull that out of the XRD pretty easily.
Yeah, it's a good first pass. I agree.
Exactly.
So I guess if your goal with this was to show that you've discovered new materials and refine those structures, I think that's where people would have a gripe with it. But that's not what you're doing. You're trying to rule out things and use it as a preliminary screening, which I think makes more sense here.
Yeah.
One thing that's interesting is even the materials that didn't match the structures perfectly, we still just matched them up to other structures at a similar composition. And the predictive results of those were still reasonably good, which was, to me, at least surprising.
Yeah, a nice sanity check.
Exactly.
Yeah, another thing I noticed is that you didn't take this filtration lightly either. many of the compositions, a majority of them, you actually filtered out before actually including them in your data set. Can you talk a little bit about that? I think I saw in the paper you made about 572 samples, but only about 176 made it into the final data set. What was the decision process there?
Yeah, and while you're at it, can you elaborate on what you mean by a pour-by framework? That was a new one for me. I've heard of pour-by in the sense of sort of acid solubilities. What do you mean by that here?
Okay, let me answer the first question. So, as I said before, the goal of this paper is to map the computational analysis to the experiments. So that means we want the materials that we experimentally synthesize to be as close as possible to what we are modeling computationally, right? So for that, we did the study in two phases. One, which is we synthesized materials and then we characterized them. And we said, okay, do these look reasonable? And if so, then we did the testing. So if after we did the characterization, it looked like it was obviously multi-phase or it oxidized, something along those lines, then we're like, it's probably not as useful to then do the testing on. That being said, we still did do a lot of testing on things that were that looked like they were multi-phase or maybe had a little bit of oxidation because we thought that the oxygen might fly away during the catalyst process itself. So there is a lot of those samples still in there. And I think that adds to the richness of the data, to be frank with you guys. You don't want everything to be absolutely perfect. So that's the thinking that we were going through. And also a lot of the synthesis, it went back and forth a lot. IK, VS Particle, and us. I mean, we met every single week at 7:30 a.m. My time to kind of discuss, how could we improve the synthesis technique? How could we make this better? And that process really helped a lot. In that.
Yeah, and I do need to mention that in the beginning, there was this long period where we just were trying to get things up and running, and of course, we synthesize them in Delft, and then we need to ship them across the globe to the University of Toronto. And I think we have been spending 3 months on figuring out how to get those samples there without oxidation problems. And that is such a funny story that the first samples we sent, I think they were oxidized. So then we were, oh shit, we need to find some solution. So then we bought a relatively, let's say, high-end packaging system that could package under argon or nitrogen. And then we did all kinds of these tests, and again, they ended up being oxidized. And in the end, we figured out that if we just package the system in air, that we will have the least amount of oxidation issues. And that took us three months. So we also did a lot of XRD analysis in Delft to really find a solution to this problem.
Super counterintuitive.
Yeah, we still don't really know why this is.
If it works, it works. Yeah.
it makes our life a lot easier. And
absolutely.
I think it enables us at some point to really crank up the number of samples. And I think we are very happy about the total number of samples that we have been able to generate towards this initial publication.
One thing I noticed in the paper was a mention of doing replicates on these, which makes a lot of sense in high throughput, right? You're automating this, and presumably the assumption is that these are more consistent, but it's good to actually show that. And so I wondered if you could go into how reproducible a lot of these experiments were. Was using these technologies in this automated framework, did it really ensure the consistency that you were after?
I would say that the consistency was the least on the material synthesis side, even though I do believe that the reproducibility of our process, our spark ablation process, is already higher than most wet chemical processes that are completely irreproducible. But still, we have seen that for some elements, and why we don't know, we were hitting the targeted elemental composition quite closely, let's say maybe a few percent atomic percent deviation. And for some elements, we were, let's say, 15, sometimes even 20% off. I do want to emphasize that is one of the most important roadmaps at the moment within VSP, is to fully optimize the process that we can guarantee a plus or we stay in between or below 3 atomic percent every time you want to print a different composition. And especially in this study, we went up to 3 elements. Within VSP, we are already going up to 4 different sources per printer, and we would like to go up to 8 maybe at some point. And then, let's say, the stability of a single source is even more important because, those errors, they add up. But we do believe that we need to stay at least below the 3% atomic percent variation, because that seems to be that something is still the same phase that you are targeting.
And it's worth mentioning that for a lot of really important catalyst materials, like people spend decades trying
Oh,
to
yeah,
get the
dude.
exact composition. So to get to that, high accuracy and getting that close to your targets in a high throughput scheme is pretty remarkable.
Yeah, and I think also for us, this work or the possibility that Meta gave us to really synthesize hundreds of materials gave us a unique possibility to learn also a lot ourselves about the process. And along the way, as Larry said, we have done many iterations about how can we improve it. In the beginning, we were printing the wafers in separate batches to the GDEs, and then we were able to hit certain compositions in the wafers, but it's with this, let's say, plus minus 10% variation, it's almost impossible to reproduce the exact same compositions on the GDEs. And then we figured out, okay, then maybe we need to print them at the same time. So then we went to printing the wafer samples and the GDE samples at the same time. And then every sample we print is basically 5 layers of nanoparticles stacked on top of each other. And then we switch between the wafer and the GDE in between the layers. So we print a single layer on the wafer, another layer on the GDE, another layer on the wafer. And by doing that, we are spreading out any fluctuations in the process across those different samples. And there is still a lot we can do in that direction to even out, let's say, any irreproducibilities of the process. So that's something that on our side, we feel responsible for on testing and improving. And also, I think I really want to say that the fact that all this data is being published is not only valuable for any other person to review it, but also is a very important step that by doing this work together, we were able, and that the fact that everything is published, again, not everything is fully perfect, but we could show to many customers what this technology could enable. And that really will help in, I think, getting quicker to standards. And I think if we are able to get our printing process to less than 3 atomic percent precision, even going up to 8 different materials, I think it's the best technology that I've seen in the past years. And I think it can really make a big difference in moving this field forward.
And just to stress one point there is being able to print like back and forth on the wafer versus the GDE is super important because we do XRD on the wafer and we do our testing on the GDE. And if they're not consistent, the experiments aren't right. So like that sort of attention to detail was super important for the paper.
One last story is that we halfway the process, I think 1/3 or something on the process, we were printing loadings of 0.5 milligrams per square centimeter. And we wanted to go quicker. We wanted to print more batches per week. So we said, okay, are you allowing us to test 0.25? And Jay Hart and Larry were open to do it. So we sent them. And apparently they even performed better, even at the higher current densities. So these things also made a lot of things possible. And I think we could even go down to lower loadings, which is also something we are seeing on the green hydrogen production part, where we are getting to 0.1 milligram per square centimeter of iridium loadings. So there are still a lot of optimizations to further speed up these synthesis procedures up.
And to reduce cost, right? Where iridium, you don't want to use a lot of loadings if you can get away with using less of it. Okay, I think we have pretty good confidence in the experimental methods for how you're measuring this, and that's awesome. Let's turn our attention to the ML models, right? So the whole principle here is you want to be able to predict new experimental data points. You're going to have to start with some data points. And I was very pleased to see that because you have on the order of hundreds of experimental data points, you're not trying any nonsense with neural networks. You're sticking to classical models, right? Because that's the amount of data you've got. But then it raises the question, what features or descriptors do you use? Your paper breaks it up into 2 camps. You want to describe the 2 different sets of descriptors that you used?
Yeah, there's 2. There's the absorption energies, in which I'm sure your audience is quite familiar with. It's just the attraction of different molecules to the surface of the catalyst. And for this, we explored 6 different small molecules. The biggest one, I think, being COCOH. So the trick there is that for every single material, as you mentioned before, has many different surfaces,
Right.
On it. So you can slice and dice a different material like numerous different ways. So we had to do relaxations basically on every different surface up to Miller Index 2 for every single one of these absorbates, and then computing the absorption energy for each one is computationally really, really expensive. So this is where like the power of the machine learning algorithms actually came in. That's where we use a neural network, was to speed up those calculations. Because if you did that just using DFT, as you know, it'd be computationally insane. But with the machine learning potentials with DFT verification, Because what we did is we took the final relaxed state and then ran DFT on that single point to make sure that it was legit. That was actually feasible. So those are let's say the descriptors that we were excited about, because that uses the ML features, etc. But whenever you do a study like this, you want to do the obvious thing as well. And that's what we refer to as the map minor features. And those are, simple features like which elements were part of the material. It's things that are properties of the bulk material itself, but not properties of the surfaces. So they're, I would say, kind of more generic features, but we wanted to see how well they perform, because it's important that we know how much can be captured just by using simple features versus, features that are obviously much more complex.
Yeah, people that have taken my informatics class or in the literature, we often call these the composition-based feature vectors, because just from the chemical formula alone, you spit out these things, and they're related to chemical things, but not necessarily catalysis things. One would assume that with the feature engineering that you're doing, generating this very specific set of information related to absorption of small molecules, that should matter more. One of the things I was surprised is when we looked at the model performance, the actual, the parity plots are not that far apart for composition-based features versus all this amazing DFT work that you've done. Was that a big surprise for you guys?
It's a good question. Was it a surprise? I guess.
Was it a disappointment?
Yeah, I mean, obviously, I would say that it was definitely you definitely want the absorption energies to do a better job, right? Because those are the ones we spend a lot of time trying to figure out how to compute them.
And they're the most satisfying hypothetically, because they describe the process. They should be good
Exactly. But on the same side, it's not terribly surprising, especially for a reaction like CO2RR, because even, for CO2RR, there's so many different pathways, etc. Absorption energies are still crazy simplistic, if you want to model that very complex reaction. Now for HER, I had a little bit more hope that they would perform better, for that. And, just from a pure correlation standpoint, yeah, the absorption energies, outperform the simpler features by a little bit, but not by a huge amount. But where it becomes interesting is when you start looking at volcano plots.
Yeah, so in the paper, it makes a fair point about the Sabatier plots, right? So the idea behind Sabatier plots, as a non-catalyst person is going to try and explain it to you, is that you can't have a catalyst that too strongly binds the thing that it's reacting with or won't let go, but it has to kind of grab it, right? So it's usually plotted temperature on the y-axis, x-axis is usually your binding affinity. And so you want it to be kind of in that Goldilocks sweet spot. And the best materials, platinum, things like that work as great catalysts, they tend to be at the top of that sort of volcano that forms, that sort of triangle. And you show in your paper that you don't plot it in the exact same way as a Sabatier plot, because on the x-axis, what you're plotting is the principal component, but you do say that 86% of that variance is basically the absorption energy. So it's kind of like it. And you see a very similar behavior. It forms a sort of volcano, and at the top of it is what you'd expect to see platinum. And when you compare that to the map minor features, you don't see that sort of outcome. Do you want to give your opinion on what you think this could mean for catalysis and for these materials and the usability of these models?
Exactly. And just to clarify, the reason that we were using the principal component along the x-axis is you can think of these volcano plots can be, just more than just two-dimensional, they're being three, higher dimensional.
Sure.
And it's just a way of kind of taking this higher dimensional feature, which was the absorption energy of oxygen and OH, and then kind of compressing that down to a single dimension using that principal component.
I see.
So, and that was the reason for compressing that down. And then what we wanted to do is look at the trends. And the main thing we wanted to see is, does what we learned by fitting to the experimental data, does that generalize in a way that seems intuitive to the other 19,000 materials that we analyzed? And what was exciting there was that the materials that kind of were at the peak of that volcano were things that generally in the literature, like platinum, we know are good for HER. Is it perfect? I mean, no. Obviously, the correlation plots we had are not perfect as well, but it does show what I'm looking for is just something that there's a hint that the trends look reasonable.
There's signal.
That there is promise.
Without
in
a doubt, there's signal here.
Exactly. Because that's what we want to find is if there's signal, then we know we can improve these methods. We get more data, we can make further improvements. But if there's no signal at all, obviously that means we're going down the wrong path. And note that we didn't do this for CO2RR because we just think it's a volcano plot isn't really suitable, I think, for that reaction. It's just so much more complex. But for something like HER, it seemed like a reasonable thing to explore.
Yeah, and it seems like enough of a correlation to motivate follow-on experimentation to really flesh that out in a more meaningful way. like this is only going off of 179 data points, and it probably would take quite a lot more to really nail down that correlation properly. But this gives enough suggestive trends to tell you where you might start populating that data set next.
And for our listeners that are machine learning peeps, which I think are a fair number, I did notice that you did some good things with how you split it up into test and train. First, you did a leave one sample out validation, which is not my favorite, but better. You did a leave one, you called it leave one composition out, but really I think what we would call this is leave one cluster out, because you took the entire family of materials in a chemical series. So if there's, I think the example you gave in the paper is you said, okay, if it's a binary between gold and copper, when you trained it, you held out all gold copper compositions. So that's a better way to think about generalizability, which is where we should be with this ML models. We should not be trying to convince people that they're right. We should be trying to convince ourselves, which means, really stress test it, hold out things that are the most similar and see how well it does.
Exactly. I mean, doing cross-validation, you have to do it, to make sure that you're not fitting to the training data, et cetera. And then the leave one out and leave one composition out, we were thinking about it from like, how would you use these models? Because like the leave one out makes sense if you're just exploring a single compositional space and how well will the models generalize. But then if you wanted to, use the models to generalize across different compositions, et cetera, then the leave one composition out, made a lot of sense. So we wanted to have both of those, in the paper.
So I have one last question about machine learning before we wrap it up with conclusions. It seems to me after reading this paper that you sort of predefined what compositions you were going to have VS Particle fabricate and which ones you were going to analyze. It didn't seem to me like an active learning framework where you're going to test some batch at a time, 100 at a time or something, 50 at a time, and then update your model and go after trying to find new materials. Am I interpreting that correct? Because it seemed like you predefined your search space, went out and checked it. I'm curious what this would look like in an active learning campaign, actually now trying to find new materials.
We did that on purpose because we didn't want to do an active learning approach. What we wanted to do was get a kind of, you can think of it as like a starter set of experimental results, which again, back to the earlier points, we wanted to be diverse, we want, positive, negative ones. We want it to be as unbiased as possible. Because as soon as you start introducing bias to the data set and the samples that you're using, then it biases it towards like certain machine learning models. And we didn't want to do that. Now, what you just mentioned is exactly what you want to do in the second stage. Like now that you have kind of like a basis, like a
you
foundation
trust your
to stand
model.
on. Yeah, I mean, exactly. I still think we need to, gather a lot more data, to fully trust these models. I mean, for HER, we saw some good trends. For CO2RR, there's still a lot of work to be done. So I think there's still a lot of room just in the pure data collection itself. But I do think in kind of going, to that extreme, it kind of sets the paper apart as well. This is something where we want to look at it from a machine learning perspective. We want to do it from a unbiased way as possible. We want to open it up to as many different, computational machine learning modeling ways as possible. And to do that, you really need to kind of, gather your data in as unbiased of a way as possible. And that's what we were hoping to do.
So maybe now to wrap things up, we can jump into maybe some conclusions that you drew from this process. Maybe if both of you would like to talk a little about some of the biggest lessons that you learned throughout this process.
So the first one, of course, is that big social media companies are very valuable in solving climate change. That was the first one early in the process. At least the second one for me was, again, I think the proof in the synthesis that we now have a pathway forward to create this 10,000, 100,000 experimental data set in a relatively short timeline. I think if you really want to make yourself angry on this topic, you can really get the data set that is big enough to train a powerful deep learning model in 2-3 years. And especially since we see more and more top-notch academia or even industrial companies acquiring the printer to build these self-driving labs and combine our synthesis with robotics and other type of high throughput methods. I think, in theory, if you combine the data of all those labs at the same time, you should be getting there even quicker. But that was the most promising thing that I saw, especially with the example of, let's say, the AlphaFold model that proved quite high predictability. Even though this is a completely different material space and different, let's say, challenges, I think that is really promising.
Yeah, my prediction is that you're going to see a lot of more business after this. I think people realize how powerful a tool this is, how reproducible it is. the capabilities. So probably a good time to be at VS Particle.
Yeah, and maybe one comment to make to inspire also people in other fields is that, as we also discussed in the previous podcast, is that the material as printed is the highest nanoporosity that you can get on Earth, because we can just make the smallest nanoparticles. But it's not that difficult, because they are very small, to melt them together and to make more a solid type of layer. So also, if you want to look for high entropy alloys for fusion blocking materials that can withstand extreme heat conditions, I think you could also at least screen the material space effectively with these tools. So I think that there's much more speed that we can bring to other fields than just electrocatalysis. I also would like to mention and do a big shout out to all those companies that are taking the next step. Let's say Nitrovolt as an example, trying to really scale nitrogen reduction to ammonia and really bring it to farmers out there. And there's also a field that we really would like to support, helping those companies to just eliminate their frustration in making these nanoporous layers on larger substrates. So that's also something that we would like to see in future work, is to really bridge this from this high throughput screening all the way to testing on, let's say, relevant large scale multi-cell type of systems.
How about you, Larry? Any takeaways from this study?
The first thing is that synthesis is really hard.
Underappreciated.
Experimental chemistry is really hard. Coming from the land of AI where things happen really quickly, it's in some ways it's refreshing, to see all the work that goes into doing an experimental paper. Machines break, like things take time. That process is a lot of fun. The second thing is that we have a long way to go in computationally modeling, these reactions. One good example is just, like we mentioned, the absorption energies, they're computed per surface, but we're studying, materials.
Oh, I was going to ask about that. If you had the ability to grow things with control of facets, for example, I think your model would have been much more predictive. The DFT data would have been much more valuable, because that was predicted for very specific conditions, but then you don't know which one you have. I completely agree.
Exactly. I mean, you can look at it either way. Like, one is that we grow, materials that have specific surfaces. The other one is we have characterization techniques which tell us which surfaces were actually realized. Because we tried so many different things. Like, we did Wolf analysis. We tried other ways of figuring out which surfaces were more important. And if you ask me what was the most disappointing thing to me was that the best way of aggregating the surfaces was to take the average.
Yeah.
I mean, like, you want it to be more exciting. You wanted to do, you wanted a more exciting answer to that question. But like right now, the average works. So there's got to be, but that's not going to be the final answer. There's got to be a better way of doing it. So, if I was, thinking about it from a computational perspective, I think there's so much richness and so much more areas to explore. Like that to me is like really exciting.
Well, maybe on that note, we can wrap this episode up.
Now, maybe.
Oh, yeah, more you want to say?
Yeah, maybe I think it's good to give maybe some direction, because I think people will hopefully use this data and try out different stuff. Is there a way, Larry, that they can approach let's say the Open Catalyst project to get it published, or to share it with the broader community, except than just making another publication? Or the other thing is that if people would like to join forces, or to join future work, is that something we would like them to do? Or so how can we grow this into a broader momentum in the community? And
one thing that we do want to do going forward is we want to do this, but we want to do it bigger. 100 data points, a couple hundred data points, it's great, but it's not going to be the amount of data that we need, to really tackle this problem. For instance, you mentioned before that we use pretty simple models. We use linear models, we use random forests, and we didn't use neural networks. And you're like, that's great, we didn't use neural networks. But the reason for that was there's not enough training data to use neural networks. We would actually love to use neural networks.
Yeah, there could be, though.
But if we could get, 10,000 examples or more, then we could start using more powerful machine learning, and maybe we wouldn't need as complex, computational, like intuition, et cetera, to do a good job. But we need to do that. We need the rest of the community to help us out in doing that. So we are looking to see, how can we scale these things up? How can we get, other places using the VS particle machine? Can we parallelize some of the testing, the synthesis, et cetera? So anything we can do to kind of and help enable the community to kind of build a challenge around this, just like CASP created a challenge for protein folding that helped that community a lot.
Right.
I think that would be super awesome, really great. And then, for the computationalists and looking at this data, obviously all this data is out there. The absorption energies on the 19,000 materials is out there. We hope that people can use this, study it, find better ways of modeling these things than what we did. We did the baseline is the way I look at it, but hopefully the community takes this on and, really takes off.
Yeah, and if people want to build on this, they want to see the data, obviously we're going to put a link to the paper in the show notes, but we'll also put a link. You have a Fairchem GitHub, basically database archive where they can actually see the data itself. So hopefully that if they're interested, they can build on that themselves.
Yeah, we tried to share everything about the experiments, all the data that we could. If there's anything that's missing, please let us know. And like I said, we have the additional computational analysis on the other materials as well. So it'd be cool to see what people do with it.
Okay, well, we'll end on that note. I'm excited for the future of catalysis. I'm psyched that bright minds at social media companies are getting involved in that and that we've got the right tools to address these problems. Guys, we'll see you next time.
Thanks.
Thanks for having us.
This episode was sponsored by the Fundamental AI Research Team at Meta. They seek to further our fundamental understanding in both new and existing domains, covering the full spectrum of topics related to AI, with the mission of advancing the state-of-the-art of AI through open research for the benefit of all.
And we are also sponsored by our ongoing show sponsor, Elsevier and the Journal Materials Today. You know that we're fans of them. They make great content. They make a great community. We hope that you'll check them out. We're also grateful for the people that make the music for this show, Alphabot, Kolobyte. You know who you are. Hope that you check out their music. We think it's great. And as always, we would love if you'd give us a review, especially on iTunes, because currently right now, I checked last night, we are in the #1 spot in the chemistry rankings. Makes me feel so good. Sorry, chemists. Material scientists barging in, taking your #1 spot, but I'm so happy about it. So give us those reviews, keep downloading these episodes, and we will be grateful for it. Obviously, if you've got an idea for an episode, we'd love to hear about it. Shoot us an email, materialism.podcast@gmail.com, or you can find us on Instagram or Twitter or pretty much wherever. We'd love to hear from you. See you next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.